Good morning. So today we will talk about bifurcations in the phase plane. So if you remember, we already studied bifurcations in the third session, but on a line, so in one-dimensional systems. And it was very important because we saw that by changing a parameter, is it possible to make fixed points appear or disappear. So we can have a system that accounts for three fixed points, two attractors, one repeller, for example, and suddenly they all collide, and they afterwards they disappear. Okay, so there is things that can happen, and then can actually characterize a system. You can also have hysteresis. So if you remember this example of the outbreak, where you have these bollworms completely defoliating some trees. But now things are even more interesting because we are now in two dimensions and we can have actually oscillations. And this is actually maybe even more relevant or a very wide field for us, for the engineers, because we can understand how changing a parameter can somehow create vibrations or make them disappear. And this is of very highly concern for us, for engineers. So this is nothing different from what we have already seen. So this is structural change of the phase portrait. Now we have a two-dimensional system, so we have actually a two-dimensional plane. But these trajectories are characterized or somehow are defined given some amount or some kind of fixed points. So changing the fixed points changes the topology of the phase plane, and this is what actually a bifurcation is, when you just change, create, destroy fixed points, collide them, and so on. This is what we want to talk about. And then we start with the first of them, which is the saddle node bifurcation. This is something we already saw in one dimensions. And also we can see that through these kind of bifurcations, fixed points are created or destroyed. And if you remember, this is the way this is represented with this equation, okay? Something that is also of interest and also of help is that most of the time bifurcations occur in one direction. Therefore, in this case, in this model, you can see that this is actually what we had already in one-dimensional systems, and this is just an additional 2D, so we have an additional direction, but it's very simple because it doesn't depend on x. Okay. And this is how this bifurcation is depicted in this figure. Okay, we have two fixed points and they collide and they disappear. So just remember the case in 1D. In the 1D we had this x, we had here x dot, and then we have, for example, let's assume we have this kind of curve, and then we just change a parameter and this curve shows up, and then you have a fixed point that happens and that is actually half stable, and then you keep increasing the parameter, and then suddenly you have, instead of one fixed point, you have two fixed points, one that is stable and one that is unstable. So this is like the way you can change the parameter, let's say mu. Okay, so this was for 1D. So remember that this is somehow the way you should imagine this in your heads. In 2D, it's similar because basically what happens is that this parameter that makes these two fixed points collide and then disappear because we're following this kind of shape as well. Okay, I will just erase this because this is 1D, so it was just for an example. Well, Now something to take into account is now that we can actually understand why this is called saddle node bifurcation. In 1D wasn't obvious. Now maybe things are more, let's say, straightforward, because now we have these two fixed points. They have actually names. So this is a saddle and this is a stable node. Okay, so that's why they're called saddle node bifurcation. What else? Something that is interesting also to see is that when you have this fixed point gone, so again I will just maybe refer to the 1D case. Imagine that they have the curve here, but it's very close to the axis. So if I move this curve upwards a bit, I will have a fixed point. Okay, but right now there is like a distance epsilon, and this curve is almost there, but the fixed point doesn't exist. However, what is interesting is that the influence of the fixed point or of this distance that is very close, it already is happening. The effect is something that is called maybe slowing down, which means that imagine you have a particle, and this particle has a given rate of change which is negative, is somehow large negative, so I want to say, and therefore it will move in this direction. But when it goes and is approaching the axis, then the rate of change is gonna be every time smaller and smaller, and then you will have something that is a particle that is slowing down almost to a steady state, to zero, and then after a certain time it somehow like escapes and then just keep moving. So this is like a bottleneck, and this same bottleneck is what is actually here depicted with this ghost cloud, which means that the effect of the fixed point is still there. This fixed point doesn't exist, but this is a region of a slowdown. You have this bottleneck happening here. So that's actually how you can recognize this situation. And this saddle node bifurcation, so in 1D you saw that it was basically something, one curve was gonna be like this and the other curve was something like this. Okay, so this was actually the function that we were evaluating, and this one was the x-axis. Okay, and we just play with a parameter mu to move this curve upwards or downwards, and then we were talking about saddle node bifurcation. In 2D things are somehow nicer because it's actually described by, instead of here having this x-axis, we have actually two null lines. Remember that we already saw what a null line is. So a null line is a function that satisfies that either you have x dot, so the rate of change in x is 0, and you can just somehow recognize this expression of having a y equal to a function x equal to 0. So this is what I'm talking about. Or in addition, so we have the one in y direction. Okay, so this is something we saw last time, and we also recognize that when the two null lines they somehow meet, we find what? Yeah, fixed point, because in this case simultaneously you have x dot and y dot being equal to 0. So in this case we have the fixed points. Okay, since this is actually a null line, so when we have x dot being equal to 0, it means that we don't have changes in x, but only we have changes in y. So this is actually already This is not correct, isn't it? This is actually wrong. Now if I change to this, so now changes in X are not allowed in F, so only in Y, and in here like this. So my question is, now that I changed this slope of the arrows, is this correct, or is this something wrong in there? Actually, it's wrong. If you remember, something that is important to know is that the direction of these arrows will change and after meeting a fixed point. So in this case, we have two possibilities. So either we can have here this pointing downwards, pointing upwards, pointing downwards, and like this is something that maybe could happen. So by looking at this, you could say that this is actually a saddle, because you will have an again direction just in your minds, maybe something like in here being repelling, and one again direction that is attracting. So you can tell this is a, a saddle. But I remember that these eigen directions we will have to compute it with the Jacobian and so on. So they do not correspond at all with the null lines. This is something different. And this fixed point, you have a stable node, or we can have the opposite example. We just change here the direction of these arrows. Okay. So depending on the arrow, you can have this picture in your minds that this is still gonna be a saddle. You can see that this is like you will have somewhere in here the eigen direction that is attracting, and somewhere in here like the eigen direction that is repelling. Okay, so this is gonna be still a saddle. But in here you also can imagine that this is actually an unstable node, because you will have somewhere like two eigen directions that are repelling. So this is like somehow very imaginative picture in your minds. Okay, in order to have something more exact, we have to do some calculations. Now we add an additional degree of freedom with a parameter mu in these two null lines. So we will make them now move with respect to each other. So now the blue curve is moving like upwards to the left, and now you see that these fixed points that now we are representing here, so this is going to be the saddle and the node, they are getting closer and closer. So this is just a representative number that just to denote that we are changing mu, and eventually you will see that we will have here in this case a half stable node. And then if this blue curve keep moving like in here, then we'll have a ghost because there is not a fixed point anymore. But we can have this bottleneck mechanism or phenomenon in the phase plane, as I pointed out before. Okay, so let's do this example. It's a very interesting one, and you can already see in here in the two equations that we can actually express this. So the corresponding equation D is equal to 0 to obtain the null line for x dot, so y equal to ax, for example, and the other one is also easy to decompose. So let's go do it. So we have two directions, so let me just put this in red, this one in blue, and then we start with the first one. So we say that x dot is equal to 0, so then we have y equal to ax. And also you will see that this is going to be useful. So when it's going to be larger than 0, so this is going to be larger than 0 when y is larger than ax. And now we go with the blue. and we say y dot is equal to 0. Therefore we have y equal to 1 over b x to the square 1 plus x to the square, and y dot is larger than 0 when we have y is smaller than 1 over b. Okay, now we draw this, so we will draw the null lines. So this is x, y, and the first null line is super easy. It's just a slope, so just depends. The slope depends on a. Okay, so this is gonna be y equal ax. The second one, okay, it's a little bit more complicated, but we can just do it in Desmos, for example, to plot it, or you can just do spend some time doing the analysis. But just believe me that it's something like this. And this is gonna be y. So this is already written in here. Okay, let me just write it in here again. So based on this, the first thing we can do is to find the direction. So this is something we already did before. So for x dot being 0, there are only changes in y allowed. And for y, for the second null line, only changes in x that are allowed. Okay, this is a little bit complicated to draw in here. Well, we have two additional things. We have already two fixed points in here and in here. We don't know yet what they are. And now we plot the direction. And the direction can be just done by using these inequalities in here. So we know that x is going to be positive above the red curve. So we will have positive in x above, and below is going to be negative. And for the red curve, for the blue curve, so we have to go below to have a positive direction in y. So this is going to be positive in y, positive in y, positive in y, and this is going to be negative in y, negative in y. So I will just draw the corresponding arrow. Remember that the components, so the length of x and y vectors, this is completely an schematic draw, so they are not exact. Well, I will just erase now the components to make things clear. Okay. Okay, and now we can just point, so draw the corresponding arrows in here. So it's gonna be more clear. So this has to be positive. This has to be negative. Okay, we just follow the flow in here. They have to be also negative. In this direction, they have to be in this direction as well. In here they have to be positive. In here they have to be negative. Okay, this slope is a little bit like supposed to be x equal to 0. The slope has to be 0, sorry. So y dot equal to 0. Okay, just be aware about that. Now that we have the complete picture, we can say with certainty, or the first thing we have to notice is that we are good because the direction along the null lines changes after the fixed point, as we already knew it had to happen. But this is going to the left, this is going to the right, this is going to the left again. This is very nice. The second thing we have to realize is that the role of these two fixed points. So in this case, we can see that this is actually like a stretching. So you see these two lines in here. So we could maybe think that this is somehow pointing the eigendirection that is a repeller. So we may think that the eigendirection should be somewhere in here, sorry. Should be somewhere in here. And that's gonna be for this fixed point. And the other eigendirection may be somewhere here, where we have actually an attractor. So it means an attractor eigendirection. So this is gonna be a saddle. And this one, you can see that all are pointing inwards. So we may have here an attractor. So let me just draw this. Okay, a little bit super big this node, sorry. Okay, what is now the purpose of this? We saw that we could have this phase portrait drawn with the classical method we already know, that is computed the Jacobian, having the eigenvectors, the corresponding eigenvalues, so that we have actually the eigendirections for each fixed point, and then plot the corresponding arrows close to these fixed points. We could do that. This is an alternative, and this alternative is actually easy to perform when you have a clear function that define the null lines. That in this case, this is pretty simple. So this is explicitly in y, so it's easy to plot. And we have here the null lines. And also we can see or analyze the case of the bifurcations. Imagine that we want to just change a. So a is going to be the parameter to change in the bifurcation. So it means that this slope in here will increase little by little, and you can just see that there is going to be a moment in which this slope is going to be tangent to the blue curve. At that moment, we will have these two fixed points colliding into a half stable point, and for larger values of a, so the slope is going to be larger, and then we'll have a line that doesn't touch the blue line anymore, and in that case the fixed point is gone. And this is a very somehow simple way of analyzing this saddle node bifurcation by plotting the null lines and to see how the null lines evolve as you change a parameter. Actually, I completely ignore one fixed point in here, which is, you can see the direction that is pointing in this and in here like this. So you can see that this is actually an attractor. So we have an attractor, a saddle, and an attractor. So with this analysis, we somehow figured this out. And we will have this being an attractor forever. So even if this slope changes so the A changes, so this is gonna be keep being an attractor. Now let's show here the figure that corresponds. So this is also in the book of Strogatz, how the phase portrait looks like if we plot instead the eigenvectors, so the eigendirections with the corresponding values of the eigenvalues, just to see if they are like an attracting the eigendirection or a repelling eigendirection. How does it look like then? And here it is. So we have the attractor, the saddle, the other attractor, and you can see that this one that we thought this had, there might be like an eigendirection in this one. It's actually, when you compute the actual eigendirections, you see that we are not far away from that representation. Also, this eigendirection of this attracting eigendirection for the saddle is clearly here. Maybe you can imagine this. Okay, there are another eigendirection in here for this attractor. You can see. So here is not super well maybe plotted because this is an scheme. And also the eigendirections for this attractor. Well, the other one I don't know how it is. Maybe something like this, and we'll have to compute it. So the idea of this was, so this exercise, to be able to, also to observe that we are able to actually recover the phase portrait just by using null lines without the necessity of computing eigendirections and eigenvalues. But this is not always the case, okay? This is just because these functions were amenable to do that. And second is that, remember that for this saddle node bifurcation, when you have a parameter that changes the bifurcation parameter, you can actually see the structure as the null lines being also a function of that parameter. So that parameter could be, for example, A. So you can just see the whole thing in your mind by looking at two null lines that move respect to each other. And then depending on that, you have intersections and the collide or the disappearance or the production of fixed points. Okay, so that was the idea of this conceptual example. Okay, this is another example, and the idea is again to find how things change if I change a given parameter, which in this case, okay, just explicitly given by mu. So you can see that in here the concept of null lines is not super helpful because we don't have a given function of y with respect to x for x dot equal to 0, so it doesn't exist. But the nice thing of this existence is that you have like two independent directions. This x dot depends only on x, y dot depends only on y. So this is a very simple example, and we can just make use of the classical understanding of Jacobian eigenvalues and eigenvectors because we will have a diagonal matrix already. Okay, diagonal Jacobian matrix I meant. Just something else before going to the actual example. Here we have considered by definition that all the parameters, so what we have seen so far and right now, all the parameters are real numbers. Okay, and we also have considered that the directions x and y are real. Still, we can have complex situations, complex numbers, but the complex number will be somehow only given to the eigenvalues, because the eigenvalues, so if they are complex, then you know that there is a part that is the growth rate and the other part that is, or this associated with the frequency of oscillation. So this is something we already saw. But mu, x and y, they are real. Okay, so if we do the things in the classical way, we just need to find the fixed points. Okay, so the fixed points is gonna be for y dot equals 0, then we have that y is equal to 0. And for the second one, so if we have x dot equal to 0, so we have just x mu minus x to the square equal to 0. Therefore we have one possibility is x dot equals x star equals 0, and the other one is gonna be x star equal plus minus mu. Okay, so we have three fixed points. We have fixed points. Let's put it in here. We have y x 0, but also we have y star 0 and x star minus mu, y star 0, x star mu. And this is very simple, very simply plotted. So let's do that. So we have here the fixed point 0, 0. Here we have the fixed point mu 0, and here we have minus mu 0. Okay, so let's compute now the Jacobian. So the Jacobian is gonna be, so the f, let's start with this one. The f dx is mu minus 3x squared, 3x to the square. Then we have the f dy, this is 0. Then we have dg dx is 0. And then we have dg dy is just minus 1. Okay, so we have the Jacobian for the three cases. So let's just write them. Here is the easy one, so it's mu 0, 0 minus 1. This one in here is mu minus 3 mu, so it's gonna be minus 2 mu. 0, 0 minus 1. And in here is actually the same. We'll just put it in here. Minus 2 mu, 0, 0 minus 1. Okay, and now with the Jacobians, which are diagonal, it's very simple to find the corresponding eigenvalues. So let's plot this with blue. So the first eigenvalue in here is just mu, so mu is a real parameter, so it's defined as a real parameter, and we will assume in this moment that is positive. Okay, so we assume that it's positive, so that we have here an actual real fixed point, x star. In that sense, we will have a eigendirection in here that is repelling, and the other one in here that is attracting. Okay, and these two here are two attractors, so two eigendirections that are attracting and two eigendirections that are attracting as well. So we will just discuss in a minute why this mu has to be positive. Well, for this scenario, mu is positive. I will just write it in here with yellow. So this is the scenario when mu is positive. But remember that mu is a bifurcation parameter. So eventually, so this is the bifurcation, like the axis. So we are right now in this region when mu is positive. Now imagine that we start reducing the value of mu. So we start from here And in this here we have this scenario, but now we start reducing mu more and more, and this mu goes closer to 0. So what do you expect? You expect that this square root of mu minus square root of mu, they will get smaller and smaller, and the distance in here will every time decrease and decrease. This fixed point doesn't move. What changes in here is that this direction that is repelling, every time is gonna be still repelling, but in a weaker way, so not as strong, because mu is also decreasing. Okay, so the changing the value of mu is changing the position of the fixed points, so they are getting closer to each other, but also it's changing the strength of the again directions. In this case, this strength is going to be weaker. Also, this attracting the strength is going to be weaker, and so on. Now, when mu is exact equal to 0, these three fixed points, they collide. You see that the square root of 0 is 0, so all of them are going to be in the same place. And we will have this again direction is still being negative, and the other again direction is actually mu 0. So this is like you had no strength of this, so the eigenvalue of this direction is going to be 0 also for these ones. And then when mu is smaller than 0, then these eigenvalues now will point inwards, so there will be, here mu is negative, it's going to be 0. You have just one node, which is going to be an attractor, and these two stable nodes, since are defined as the square root of mu, then they will be imaginary and they do not exist in the real set of numbers, that is where the x and y are defined. So they do not exist. And we look at actually at the plot of the complete plot. So this is what we just discussed. This is the case when you have the mu is more than 0. So you see that this saddle becomes a repeller, and the other fixed points, they do not exist anymore. And here this is very close to this one. Okay, but just to point out, this again direction in here is not actually, this is a negative again direction. This is a negative direction that we actually realize that is 0. But if you go and you plot it numerically, you will realize that you still have an slowing down phenomenon. Even if the again direction is not there, it's not negative, you will see that you will still have like a phase portrait where the trajectories are associated with a very slow growth rate in x. To analyze this, we will have to consider something more than a linearization. Okay, so we will have to consider second order terms to analyze that critical slowdown in this particular case. Okay, so let's go to another example. This one is very interesting. You will see why, because actually the question somehow is different. The question is now, show that a supercritical bifurcation occurs in this system. Okay, or just explain if this is the case or not. So it's not just to show the bifurcation, but it's to show the class of the bifurcation, so the type. Okay, so let's remember what a supercritical bifurcation is. So it's when you have, at a given moment, the origin is stable, and then the origin loses stability and becomes unstable. So remember, this is the dashed line that represents this, and at this point the bifurcation, so the critical value for mu, then you generate another fixed point. So this is a representation of this case. Now this is a supercritical. So remember that we talk about this as the bifurcation that is safe, which means that we can know at a given moment to stop and go back to the case. In this case, let's assume this is a parameter, so this is going to be x, and we want x to be 0, and then if x goes beyond 0, then we are able just to go down, reducing mu, and going back to the desired case, desired value of x. And you see that we don't have hysteresis in this case. Now if we go to the subcritical, this is the dangerous one. So we may have again this is the same origin, the same equilibrium at x equal to 0. Then we lose stability, but now we will have another fixed point in here which is going to be unstable. And remember that eventually we could add higher order terms to have another fixed point in here. So there is this jump, remember, of the subcritical bifurcation. So the idea is we will just place ourselves at the origin of this system and show that at the origin we have this kind of bifurcation and not this one, or maybe the other way around. Moment. Okay, so what do we need to know? Let's somehow frame our problem. The first thing is that we will analyze the bifurcation at the origin. So it means that we will need to understand, the first thing to understand is the stability of the fixed point at the origin. Okay, so we will need to do what we already know, which is just first of all formulating the Jacobian at the origin and finding the eigenvalues. So this is gonna be with the eigenvalues. And we need to know this for maybe different cases. We can have it for mu smaller than mu critical, and for mu larger than mu critical. Okay, so and for mu equal to mu critical as well. So basically this is what we need. And also the other thing we need to know is the existence of adjacent fixed points again for mu smaller than mu c and mu larger than mu c. So by doing so, we will analyze what we just draw just before. So imagine this is mu critical. So first of all, we will analyze how the stability changes after mu critical. So here, if we need a dashed line in here or a dashed line in here, so what is the direction of the bifurcation? And the second thing we need is to know that how many fixed points we have before mu c and how many fixed points we have after mu c. Okay, so that also helps us to understand the kind of bifurcations, if it's supercritical or subcritical. Okay, and another thing that you may now question is, we will use the method, the classical method of having computing the fixed points, and from the fixed points computing the corresponding stability, actually only the one of the origin. Okay, so let's find the fixed points. So we will have x dot equals 0. Then we have mu x plus y plus sinus of x equals 0, and y dot equals 0, which means y equal to x. So we can already replace this one in here. Then we will have mu x plus x plus sinus of x equals 0, and we just factorize x, which is gonna be x mu plus 1 plus sinus of x. So if we solve this equation in here, there are already many things to say. First of all, we will have the expression for x with respect to mu. So we will know how the fixed points depend on mu. And we will also see that we have an infinite amount of fixed points. Okay, this is a transcendental function, and that actually makes things complicated to make the factorization of x. Okay, so basically the idea right now is to somehow simplify the problem, because we cannot just have a straightforward formulation for the fixed points and around the origin, which is the one we're interested in. So what do you think is going to be a good strategy? Remember that we only care about what is happening at the origin, okay, or very close to the origin. So in these cases, when you are deriving, for example, this kind of models that give you some transcendental functions, well, the idea is somehow a Taylor expansion. So if you do a Taylor expansion of this sinus of x, then we will be able to just have a polynomial representation of this sinus of x, and also we will be able just to truncate the series and maybe a lower order polynomial if we don't want to be too exact, or if we don't want to cover a very large region of x. So we will just get very close to the origin, which means that we will do a Taylor expansion around 0, which is the origin, x equal to 0. Okay, and we will see how many terms, which is the expansion order that we need to do our work. Okay, so let's remember what is the Taylor expansion defined. So we have a given function f at the expansion point, plus a given value, and then we will have this is going to be approximated to f x0. Then we have the distance, so it's going to be delta x, so x minus x0. And what is next? So just try to send me your ideas. Okay, I think I get one already. Is the first derivative of f with respect to x evaluated where? Yeah, at the expansion point, x0 plus, then you got the second term here is divided by 1 factorial, this is divided by 2 factorial, and then we have the second order derivative. And actually, because I have already did this example, I know that we need the third order expansion, we will see why. So this is 3 factorial is going to be 6, and the derivative x0. Now if we go and we say we want to have sinus of 0, so expansion point at 0 plus x, then sinus of 0 is going to be 0 plus delta x is actually x, because yeah, your x minus 0 is equal to x, and the derivative of sinus of 0 is what? The sinus of x, sorry, is going to be cosinus of, and evaluated at x0, so cosinus of 0 plus x to the square over 2, and this is the derivative of the derivative, so it means the derivative of cosinus is going to be minus sinus. So I have to just change here the sign here, 0 here, and then the derivative of minus sinus is minus cosinus, and then we have here the higher order terms. Okay, so basically we are saying that we replace sinus of x by x minus x cubed over 6. So we will replace this function by this one. So instead of having an infinite amount of fixed points, because there are infinite amount of roots for this function, we will consider only how many roots? 3. Okay, and this is going to be introduced in here or in here to find the fixed points. Okay, now we just have to replace this, oh god, this in here. Okay, so let's do that. Mu, let me just do the one above, mu x plus x plus x minus x cubed over 6 equal 0. So we need just to factorize this. We will have x mu plus 2 minus x to the square over 6. Okay, so let me revise. Mu x plus, yeah, okay, so I think this is correct, and we need just to find the fixed points. Again, we're in this fixed points evaluation. So we can have one fixed point at x star equals 0 already, so here, and the other one is going to be by solving mu plus 2 minus x to the square over 6 equals 0. So we just organize this, and we have x is over 6 is equal to mu plus 2 and plus minus square root. So right now we can actually talk about the stability. Oh no, maybe let's talk about first the existence of this fixed point. So as I told you before, all these parameters are defining the real set of numbers. Okay, therefore we need that this term in here is positive. So let me just do this. I will just write it in here. We need to have so we need two cases, mu, this is going to be mu less than mu c and mu larger than mu c. But what is mu c? Is the value of mu from where we go with one fixed point to more than one fixed point, okay, or where the fixed point just disappears, so something happens, okay. And we can see already that when mu plus 2, so mu plus 2 is larger than 0, we have something happening. So when mu is larger than -2, we will have the creation of new fixed points. So this is actually the critical is going to be -2. So we can replace this mu c in here already. And put -2. So this is the critical gain. I will just put it in here. Mu c is equal to -2. So what happens when mu is more than -2? This is going to be a negative number. Therefore, we will have these x points being imaginary, which, since these are defining the real numbers and the real set of numbers, so we say they do not exist. The only fixed point that exists for mu is more than -2 is x star equals 0, okay. On the other hand, when mu is larger than -2, then this becomes actually real, and we will have, in addition to this fixed point, we will have these new fixed points. So I will just put it in here. So we have x star equals 0, and here we have x star equals 0. We also have x plus 6 mu plus 2 and x equal -6 mu plus 2. So now we have 3 fixed points. So how does it look like in a bifurcation diagram? So we will have x, this is mu, x, and this is going to be here mu c, which is actually -2. And we know that in here we have one fixed point, in here we have 3 fixed points. So we don't know Lucio, but let's assume it's something like this, okay. We have a negative, this one, 0, and a positive one. So from this one, do you think we could say we have a supercritical bifurcation? So maybe you could do that would be like a mistake, because we could say, yeah, this is the origin, and then we just go in here and we go back, there is no hysteresis, okay. But remember that we haven't evaluated the stability, so there might be some dashed lines in here. We could have, for example, a subcritical. Imagine if we are actually, if this is unstable, if this is stable and this is unstable and this is unstable, so this branch and this branch is unstable, then actually if we go from this direction, we will have a subcritical bifurcation, okay. Is this subcritical bifurcation because we are looking if mu is coming from the right to the left, so just to make it more clear. So what do we need now? We need to evaluate the stability, and we will observe that we just need to evaluate the stability at the origin to be able to give also or to assess the stability of these two branches in here. And this is simple because the stability of the origin is easy to compute because x equal y equals 0, and then calculations are easier. We need the Jacobian anyway, so let's do the Jacobian. Okay, so let's write the Jacobian for this case. So the f, the x, so we just look at this equation in here. We have mu plus 1 minus 3x squared 6. Df dy is going to be 1. And here is very simple. Here is dg dx is going to be 1, and dg dy minus 1. Okay? And the Jacobian at 0, 0, we have mu plus 1, 1, 1 minus 1. So just remember the formula for the eigenvalues. So we have lambda equal to tau plus minus tau square minus 4 delta over 2. And what we have here, we have that trace is what? Yeah, the trace is just the sum of this plus this, therefore we have mu. And delta is the determinant. So this multiplied by this is minus mu plus 1 and then minus 1. Okay, which is actually this is minus mu minus 1 minus 1, then it's minus mu minus 2, which is just minus mu plus 2. Okay, just organize some stuff. I move things to the left. There's a in here as to have more space. And now let's replace lambda equal to mu plus minus mu to the square minus 4 mu plus 2, actually plus, delta is minus, so it's plus, yeah, over 2. And now let's analyze this term, so this expression. Let's consider first this case when mu is less than minus 2. Okay, when mu is less than minus 2, so here we have something giving us a hint that it can be actually an attractor. But how can we actually know if it's an attractor? I mean a stable node, so with two eigendirections being associated with a negative eigenvalue, or if we have a saddle, so we have one with a negative eigenvalue and one with a positive eigenvalue. So if we know that mu is smaller than minus 2, we also know what is the role of this. So this quantity is going to be negative. If this quantity is negative, it means that this quantity is smaller than this. Okay, so let me just put it in here in words. If mu is smaller than minus 2, then mu is larger than mu squared plus 4 mu plus 2. because remember we are just subtracting, so this term is negative, therefore we are just subtracting something that at the end is gonna be smaller than mu. Okay, maybe just to avoid any confusion, I think is I need really to introduce this absolute value here. Okay, so the absolute value of mu is larger than the absolute value of this quantity. Then we have what? A saddle or a stable node? We have actually a stable node. And then we will just write it in here. We have origin is stable, a stable node. In the other case, when mu, let me just write it in here, if mu is larger than -2, then we have the opposite case. Because in that case, this quantity in here is going to be positive, so this is going to be positive, and this is going to be, this entire quantity is going to be larger than this one. Therefore, we will have one eigenvalue being negative and the other one being positive. So in here we have a saddle. Okay, so let's draw again what we have until now. So just this is the mu axis. This is -2, which is the critical mu, and here we have x. And now we know that the origin is stable for mu is more than -2. And now we could think that, okay, and it's unstable for larger values, okay. And we also know, okay, so we said this is unstable because we assume that we are now talking about the unstable branch of this saddle. Remember, this is the origin is a saddle, and we have, in addition to that, the existence of two additional fixed points. Okay, so strictly speaking, I mean, if we don't know yet if this is actually a unstable branch, because what if it's the stable branch? What is telling us? So let me just go back then and say this, we don't know yet this. Now let's build the phase plane, because this is of help as well. So here x, y, we know. Now I mean, let's remember we are talking about mu larger than -2, okay? So we're interested in this case, which is the tricky one, when mu is larger than -2. When mu is smaller than -2, this is just a stable node. So we have two eigendirections that are with negative eigenvalues, so they are attracting to the origin, and that's all, because we have one fixed point. Now the other case is this one, so somewhere in here. Now we have three fixed points, one at the origin, and the origin is a saddle, and we have another one in here and another one in here. Remember that we are talking about x is equal to y, and y is, and x is already computed by this, so this is gonna be the fixed point 6 mu plus 2, and this is minus 6 mu plus 2, and this is a saddle, okay. What is the first thing we have to analyze? The first thing we have to analyze is we have only three fixed points, okay. So these fixed points, they have to be connected by a branch. Okay, they have to be connected by a branch. And the question is, let me just draw the other branch, like this. Well, it doesn't matter much. Let's assume it's something like this. Now the question is, what is the branch that is attracting and what is the branch that is repelling? That is actually an interesting question. Let me just draw two additional branches, just somehow assuming that these are the other eigendirections of these two fixed points. And we can have this scenario. Let's assume this question, that this one is actually attracting okay, that is attracting, this is attracting. Then there is a lot of things to say, because then this is gonna be then a repelling one. Then maybe we can have something that also is repelling in this direction, and it completely changes the picture. So we could have branches coming from here going in this direction like this, because in this sense, remember that since we're in a saddle, this one will be also, that will have to be a repeller, and then we will have these points going in this like this. Okay, and this is, then in this case we will have this branch being stable and this branch also being unstable, being stable. Okay, so strictly speaking, we'll have a completely different situation. Okay, so what I meant to say is that we, in addition to the eigenvalues at the origin at this situation, we need to know the eigendirections. I mean, maybe we wanted to avoid it, but we can't. We would explore this scenario. So let's assume that we have the attractor, and the attractor, so the origin was a stable node at this region. Therefore, we had these branches being attracting, this one attracting, and these ones in here, they were also attracting in this case. When we go and we change mu to this one, then we may expect that these branches will go in this direction. Okay, so this is the other scenario we want to explore. So it means that mu equal to -2, in this position, the eigenvalue in this branch is actually 0, because before it was attracting, at -2 it becomes 0, and for larger values of -2 it becomes a repeller. Okay, so this is the scenario we want to evaluate, and let's see if actually holds. So for that one, we just need to compute the eigenvalues and the eigendirections at the exactly value of mu equal to -2. So let's write the Jacobian first. So the Jacobian was, okay, so now evaluate this Jacobian at mu equal to -2. Then we have -2 plus 1, -1, 1, 1, -1. Here we have the trace is equal to what? The trace is equal to -2, and the determinant is equal to -1, no, 1 minus 1, 0. Okay, now we go to the values of lambda. So here is tau plus minus delta square minus 4 delta over 2 lambda is equal to minus 2 plus minus 2 minus this is 4 delta is 0 over 2. So here we have that one eigenvalue is going to be minus 2 plus 2, so it's going to be 0, and the other eigenvalue is going to be minus 2 minus 2 minus 4 over 2 minus 2. Okay, and these are the two eigenvalues. But now we need to have the eigendirections. Remember, we need that if this scenario holds, we need that this minus 2 is associated with this eigendirection, and that this one is associated with this eigendirection. If that happens, this is actually the scenario that explains this bifurcation, which is going to be super critical. We will discuss it. So we just said that the Jacobian of interest is minus 1, 1, 1 minus 1, and then we will just have lambda equal to 0, and this is associated with an eigenvector v1, v2. Okay, so it means that minus 1, 1, 1 minus 1 multiplied by v1, v2 is equal to 0, which means in this case that v1 minus v1 minus plus v2 is equal to 0, which means that v1 is equal to v2. Okay, so if we can just say that the first eigenvector is 1, 1, so this one is actually 1, 1, so 1, 1, and the other case is lambda minus 2 we need to find which are the eigenvector. So this is going to be minus 2 in here, so plus 2 plus 2, and we go and do the same thing, so minus 1 plus 2 v1 plus v2 equals 0. So this is going to be minus 1 plus 2 v1 plus v2 equal to 0. So we will have just something different. We will have 1 minus 1. And this is actually good news because it means that the scenario we propose actually holds. It means that this eigendirection, which is 1 minus 1, okay, is actually associated with an attractor, which is minus 2, and this one at mu equal to minus 2 is associated, this 1, 1, with an eigenvalue which is equal to 0. But we expect then that for larger values of minus 2, then it becomes a repeller. So now that we are sure that this scenario holds for the origin, we can certainly do that this one is a repeller. Okay, a repeller, and just by definition, let's say, or not by definition, but by reasoning, we will know that this is actually, this one in here is going to be an attractor. And also this one. Which means that this is going to be a full line. And we will have, therefore, a supercritical bifurcation. And that's the actual end of the story, because we already shown that this is composed by this trajectory which is stable. We don't have hysteresis, so we have a supercritical bifurcation. I think some of you may wondering, why did I just say this is going to be an attractor at the end of the story? Actually, you can see that if we want to have three fixed points, this is the only scenario possible. Imagine, for example, that you have here, instead of having this branch, if you wanted this branch to be a repeller, then we will have here this branch being a repeller, this one a repeller. Therefore, we will need an additional fixed point in here, okay? But we don't have more fixed points, therefore this has to be an attractor automatically. And what about this one? Okay, this could be actually a repeller, so we will have like two saddles being connected, and in that scenario we will have then fixed points at the infinite, because we will have something that comes from here, maybe goes like this and goes upwards. And then, okay, it would be like a strange case, I would say. But in any case, for the bifurcation that we are interested in, we are just analyzing things along this branch, okay? And therefore we have here this origin in this branch being a repeller and this branch being an attractor, okay? So maybe you will have questions about this exercise, so we can discuss this in the class. So this is the end of the part 1 of bifurcations on the plane. We will continue next class talking about Hopf bifurcations, which are associated with complex eigenvalues. And these are very interesting because this is a way of understanding when a system can trigger oscillations or not. Remember that the complex eigenvalues are associated with spirals. Okay, so see you next time. Bye bye.